Hey everyone, welcome to the Unhandled Exception podcast. My name is Dan Clark and this is episode number 55. And today I'm joined by Oren Eini and we're going to be talking about database internals. So I'm hoping that this is going to be something we can do in an audio-only podcast, diving deep into database internals. But welcome to the show, Oren.
Thank you for having me. I'm very happy to be here.
You're most welcome. So you're the CEO and the founder of RavenDB, which is a database written in .NET, I believe, which is quite cool. I don't want to say this is a .NET podcast, but it probably is. So could you introduce yourself to the listeners and just tell us a bit more about what you do?
Sure. So my name is Oren. I've been working on databases for the past 25 years. About 15 years ago, I got really tired of having to suffer through another databases related issue. And I had this vision of I want to have a perfect database, something that would allow me to run and operate with as little hassle as possible. And it was this burning desire inside of my head to get it out. And eventually I started sketching out the design, and then I started writing some code. And then I started writing a business plan for that. And we're now 15 years later, and this has been how I pay the mortgage and do pretty much everything for quite a while.
I must admit, like working on a database code base, it feels like quite, I think my idea of a nightmare, to be honest. Like I'm just thinking about all the different things, like different hardware and software, the unlimited amount of complex queries that a user might write.
You start from the beginning. You mention hardware, and then you realize that what you consider to be the simplest possible thing, writing a bunch of bytes to the disk. Okay, this is now 3 months research process to know how to do that properly. Which, if you think about it, is utterly insane. If I'm using C# as a great example, file.write all text, one line of code to actually do that. Except that, okay, in order to do that properly and safely and in an efficient manner, okay, now you have to realize that disks are slow. They're slow in the same way that glaciers are. And in order to write to them, you have multiple sets of buffers, all of which would lie to you about, oh yeah, we did the actual write. So if you care about durability and atomicity in databases, which you really, really should as a consumer of a database, then you have to figure out how do I write efficiently to the disk, bypassing all of those caches and buffers in the middle, which turns out to be super hard because they are there for a reason, because this is slow. And when I'm saying this is slow, I'm not talking about, that old 500, 5200 RPM disk that you have in your grandma laptop. I'm talking about modern disks as well are slow. And they're slow because CPUs are fast and memory is fast. And then you have, I have to persist the data. Okay, this is now a whole different order of magnitude in which I need to operate. And it turns out that C# actually have a whole bunch of really interesting features for writing low-level code. Whatever this is, value types or unsafe code or pointers. And I'm speaking in this case, by the way, about C# as it was envisioned in the early 2000s, because I've been working on C# since then, basically. And in the past 8 or 10 years, there has been tremendous number of work in order to make C# into a better low-level language, whatever this is, the spanification of the framework, whatever this is, allowing tree syncs and all sorts of stuff like that. But even going back to the C# 1.0, it is a language that was very explicitly meant to write high-performance stuff and has the ability to integrate with low-level details.
Even forgetting about the low-level writing to the disk and that kind of thing, just like the kind of algorithms that you might use, I'm assuming using something like a B tree or something to actually how to store that data, how to quickly query it. And then you've got all the problems like you're talking about, actually writing to the disk itself, and then presumably things like garbage collection and stuff you've got to think about. All of these, so many different things you've got to think about.
Yeah, garbage collection has been a huge bane in our existence because eventually the garbage man comes and you're running there processing 1,000 transactions per second. Okay, that's nice. That's not a huge load, but each transaction generates some garbage. And at some point you need to do a GC cycle, which means that here's what's going to happen. The GC is going to say, okay, stop the world, nothing moves, I'm cleaning here. And then you go back and start working. Now, this leads to two really serious issues. The first issue is that you don't really have the ability to run on a steady state system. So let's say that I'm running at 100 transactions per second, and each one of them needs to process, let's say, 10 milliseconds of runtime. Every, minute or two, whenever the garbage gets too big, then I'm going to have a stop the world allocation. And stop the world allocation means that, okay, number of requests per second drop, latency jump really, really high. And you can see it very nicely when you're looking at your metrics and you look at the P99 metrics. Every now and then, every 1-2 minutes, I have a huge peak in latency, something that I don't want to allow. Another aspect here is what happens if you have a seriously loaded server and it generates a huge amount of garbage, or even the structure of your object graph is expensive. And that means that now you're going to spend 30 seconds doing GC. And if you're spending 30 seconds doing GC, well, what is it going to look to the outside world? Well, it looks like you're dead. So other components in the cluster are going to say, okay, we need to switch over, take over responsibility, run new elections, all sorts of stuff like that. And when we start writing RavenDB, the design of RavenDB was basically just an ASP.NET application running in IS. And it used MVC architecture from basically about as classic as you can get, when we will focus on persistent to disk and presenting you with a better mechanism for querying operation. And at some point we got big enough that those issues that I mentioned started hitting us really, really hard. And when you need to run and figure out what is the performance of the system, and starting adding caching here's a story. We added a cache to prevent going to the disk, because going to the disk is super expensive. So we have a cache, and that cache we were storing at the time documents as JSON strings. So instead of storing the data as a JSON string, we already cached that. So let's hold that as a parse JSON object. So far, so good, and we run the benchmark, everyone is happy. Except that you get into an annoying edge case. What happens if you're under load, you're running at near system capacity? Then the following things happen. You read from the disk, you parse the document, you put the document in the cache, and you may use it, you may not use it, but there is a lot of work going on, and the GC is running. When the GC is running, it's going to say, oh, this value, this document that you have is in the cache, so I'm going to move it to Gen 1 and then to Gen 2. Okay, perfect. This is what I want. Except that now I'm starting to accumulate more and more memory, and the cache is going to be dropping the responding to memory pressure, dropping values. Well, that's what it's supposed to do. Now, consider these two behaviors together. What happened is that under memory pressure, I put something in the cache just long enough for it to be promoted to Gen 2, and then I'm dropping that. Which then means that I effectively got to the point where running without the cache is faster, because the GC isn't going to need to hold much of additional work. And then you realize also that the structure of your document methods, if you have a really complex object graph, the cost of GC is linear to the number of objects that you have. We run into a problem using thread local. Thread local it's hard to explain that using audio, but try to imagine a mesh of pointers that points to one another. And it's a really complex system, especially if you have lots of threads and lots of objects. So at this point, we actually figure out that, if I create a lot of thread locals in a lot of threads, I may be spending higher than 50% of my time just tracking the thread local object graph, and then realize, I have to collect that data. As a result of that, around 2015, we went with a completely new architecture for RavenDB. And this new architecture was basically acknowledging those issues that I just spoke about. So instead of relying primarily or only on managed memory and the GC to handle that, we defined that most of the memory used inside of RavenDB is actually unmanaged memory that is controlled explicitly by RavenDB. So the idea here is, let's take memory that is being used by a request. So what do I want to do? And in this case, a request is almost always short-lived operation. So I'm allocating throughout the lifetime of the request, I'm allocating by using something called bump allocator. I have, let's say, a 2 megabyte buffer, and each time that I need to allocate, I'm going to grab the next item from that buffer. At the end of the request, I don't need to do any sort of cleanup. I just reset the last allocated position back to the beginning of the buffer. And what is nice about this is that at this point, I'm able to reuse the same buffer for the next request. And that meant in turn that the amount of work that the GC had to do was massively reduced. We also introduced a lot of work with memory mapping. So instead of having to read data from the disk, and then we are able to just access it by pointer. Now, you still have to read it from disk. It's just that the operating system does that for you using page faults. But then comes the next part about this. Instead of storing the data as JSON text on the disk, we are actually storing that in a format that is amenable for being processed using zero copy procedure. What do I mean by that? You say, give me the name property of this particular document. So you do a lookup inside of the database, and it gives me the pointer to that document in memory. This is actually a pointer to the value of the disk, but because it's moving up, I can access it directly as a pointer. At which point I have the buffer, which represents the document. Now I'm able to do, without parsing this whole potentially very big document, I'm able to just jump directly to the name feed and get that value directly. And that ended up being a really important aspect of the performance, because we still want to use C# and all of the benefits that it gives us as a high-level language, but we are able to identify a bunch of core features that were the hotspots, and we eliminated them very aggressively. Here is a really interesting details. Let's say that you want to write a JSON text to a network stream or something like that. What would you expect the cost to be if you look at the profiler? I have 100 megabyte of JSON that I want to write to I have 100 megabyte in memory that I want to write to the network. What do you think is going to be the most expensive bit in here?
I don't know. You've caught me off guard now.
Yeah. So the really, really, really funny thing here, not write to the network, not IO. Figuring out if the value that you want, the string that you want to write, has escape characters in it.
Oh, right. Okay.
So let's say that you have...
I wouldn't have guessed that one.
Yeah, I wouldn't either. And there is a reason why when people talk about performance, they're saying profile. I'm not talking to you without any profile results, because the number of times that oh, I know why this is slow. And then, oh, wait, I have a N square operation here that I could eliminate in 1 second and the performance is back on track is huge. So we've realized that writing the strings to the network, before you can write the string, you have to provide the escape characters, which means that you have to run over the string multiple times. And that was insanely expensive. We're talking about greater than 50% of the cost of writing JSONs is write escape string. So when we built the internal format, we have a way of doing that without that. And basically, tremendous amount of work around this idea. Whenever we realize that there is something that is problematic, we solve that. At the same time, I'm doing that in C#, which means that every time that I don't have a super critical performance issue, I get to use very high level features. And another really important aspect is the feedback cycle. If I'm talking about a C# application, and RavenDB is now over 1 million lines of code, I hit a 5, and within 10 seconds, I'm debugging the actual issue. If I'm using C or C++, especially C++, I'm hitting a 5 and I'm going to lunch. Because the build cycle, even using incremental builds and all of those sort of things, is insanely expensive.
I remember those days. I used to work in the games industry, which was C++, and their code base was massive. And what's it called? I think it's Incredibuild. And we had so basically there was a lot of developers in the company. So we all had it like the builds distributed, but even then it was still a wait. Have you seen that XKCD comic compiling and they're doing sword fighting?
Because there is nothing you can do. And it turns out that this is a killer for productivity. And if I can say, oh, there is a problem, I'm just going to be debugging that. Just to give you some context, I now have a problem with a terabyte dataset. After you index about 650 million documents, there is access out of bound or something like that. Okay, I don't have the machine to actually debug it locally, but I'm able to SSH the machine, attach that using VS Code or Visual Studio, and debug. Oh yeah, I forgot to account for the metadata overhead, and there is something there. I can fix that, and I can fix that and then I hit F5 again, and then I verify that this is working within seconds. And this is, over remote machines without really needing to think or worry about that. And that is an amazing achievement.
Yeah, sounds it. So do you have, regarding these changes and tweaks you make, presumably you have quite a big test coverage, like unit tests and things?
I think that the last time I looked at the unit tests, we had something of 30,000.
Nice.
And so we actually got to the point where we have so many tests that it's unfeasible to run them on any reasonable machine in a reasonable time. So we actually have, I think, something like 6 layers of tests. There is the fast test, which is about 3,000 tests, and they cover most of everything and take under 5 minutes to run. And then you have slow test, stress test, all sorts of other nightly tests that we're doing. I actually got 6 physical machines and put them in the server room. And they are 100% of the time, they're busy doing just builds. And we got to the point where we have a queue that, okay, you may see the results for this particular run, including all of the nightly stuff, only tomorrow. And it's funny because we also realized that, we had a performance cliff at one point. So one day the system performance, let's say, is 1,000. The next day it's 200. And that raises all sorts of alarms, what's going on. And we start analyzing the code. And someone changed something related to the priority of threads. So that looks very suspicious. But, you revert the change and it's still happening. And what's going on? And then we realize that we're running those machines with NVMe disks. because that's the way to go about it. And we basically run into the limitation of the write cycles of the disks. So the performance drop. And at this point now I have an emergency disk at the server room because it turns out that at our rate, we are actually burning through them on a fairly regular basis. So, okay, yeah, we have a problem. Let's look at the smart details of the drive and see what's going on there. But it turns out that getting those physical machines was actually a really good financial decision because the amortization cost of doing that versus getting a cloud instance is hugely in favor of on-premise details for that.
At the very start, when you said, and you described your background, and you said that you were trying to use databases and you just wanted something that was simple and worked, do you regret that now, thinking, this sounds so complicated?
Look, if I went back and spoke to myself, I would slap myself silly. You have zero idea what you're getting yourself into. On the other hand, from a professional perspective, I think this is absolutely fascinating topic environment to be in, especially because in many cases, your ability to leverage low-level details to get some interesting results is enormous. It's even beyond that. You know that when you have a kid going to school and they talk, I have to learn geometry or something. And when would I ever need to figure out, when would I ever need to calculate the length of the hypotenuse? I don't know how to say that in English.
Hypotenuse.
Yes, that thing. When would I need to compute that or something like that? And then you realize, okay, pretty much the entire computer science curriculum is absolutely and utterly relevant for building databases. One of the things that I love to ask candidates when I'm interviewing them is, build me a phone book. And I want to be able to search on a user using a prefix search. So I'm writing DA and show me all the Dan, Daniel, etc. Something like that.
Can we just define perfect search for listeners?
I'm trying to search on, so you have a phone book and the phone book have a phone number and a phone and the name. And I want to start writing the name of name of a contact, and I want to find that. So in your case, I'm writing DA, and it's supposed to find me Dan, Daniel, Danish, etc. And I want to do that in a way that would be achievable, even if I have, millions and millions of records. The killer for me is that this is literally CS 101. You're talking about, okay, I need a sorted structure, and then you traverse the tree until you find the first record that has these static details, then you scan over that. And anyone who ever had to implement a red directory or a AVL tree or something like that is supposed to be able to do that. And way too many people cannot do this. To give you another example, in the phone book example, I'm asking, how do you ensure that you have one copy of a phone number? So a phone number needs to be unique. How do you do that? And I obviously want to do that in a way that isn't going to be n squared. And the answer for that is, okay, I'm expected to be using a hash set or a dictionary or a map or whatever you want to call it. And in many cases, it doesn't show up to people. I have people who are, graduate, have a couple of years of experience in the industry, zero ability to come up with a solution for that.
I guess in fairness, though, the average software development job is like forms over data, doing APIs and stuff. So it's a very niche thing to even have to do that kind of thing.
You're killing me. Dictionaries and hash tables are not niche things.
Oh, maybe not those, but as in doing like binary trees and stuff. Like I can't remember the last time, or B trees. I can't remember the last time I've ever had to do anything like that.
Yeah, but I don't expect you to remember how they are done. I expect you to know that they exist, to be able to, I have a a problem, I'm going to be utilizing this to solve that problem. And it's really interesting when you realize that, okay, there is a huge mystery. Oh, there is this API, and how it works is magic. I have a terabyte data set, and I want to be able to query over that. And then you realize that, okay, I'm going to do that. It's going to be fast, but how is it going to be? I have zero idea. Seriously? And then if you think about, okay, this API, this database, the way that it works is magic, you have no way of actually utilizing that in an efficient manner. Which means that, oh, this was fast. I don't know why it was fast, but it was fast. Let's do it over and over again, which leads to cargo count and all of those sorts of things. Going back to the phone book example, a user who managed to get to, I want to be able to do a prefix search. And again, AVL tree, scan over that, that's supposed to be very simple. My next question tends to be, okay, I now want to be able to do a search. And let's say that we have John Smith, and I want to be able to search for JO and find all of the Johns. And I want to search for SM and find all of the Smiths. And basically do not a prefix of the whole name, but a prefix of parts of the name. Or I remember that it was something that ended with CH or whatever. And those tends to be, this is a jump forward. And then you realize, wait, the AVL that I had before where the key was the full name, all I need to do now is just split it into words, and that's going to be my index. And then you realize, hey, this is how full text search works. And if I wanted to do more interesting things, I can use n-grams, where I'm not splitting the data based on word boundary, but every 3 characters is its own item that I'm now able to search for and look at. And when you realize that you have those capabilities and abilities, now I'm able to do things that looks like absolute magic. Like it used to be the case that you went to Google and you search for something and it would find you what you meant, not what you searched for. Today, you're getting what someone paid for, which is a whole different topic. But I remember being absolutely amazed by the accuracy in, I didn't know how to say that, but this is what I was searching for. And then you realize that, okay, if I want to do the same thing on my end, how complex is this going to be? Let's say I have a CRM system, and I want to be able to do a lookup of a particular customer. So I have the ability to give you, here are the 10 fields that you can search on, which may be, order ID, customer ID, contact, whatever. Or I can give you one field which would search over all of them. And the way it would search over all of them is basically, okay, you're going to aggregate all of the fields, all of the interesting fields from the document and put them all into a tree and then look up based on that. And this is really, really simple. And we're talking about, if I'm writing that in pure C#, doing that in memory, we're talking about less than 50 lines of code. But the results of doing that is going to blow people's head off. And again, this is not magic. And this is stuff that we have been dealing with as an industry for a very long time. And then you get to the realization that the amount of, again, using the database field, there has been tremendous amount of research and publications and information on that. So there is a professor in Quebec, I think, his name is Daniel Lemire, and he writes about performance, and he does really, really, really crazy things, which appears to the outside world like utter nonsense. One of the things that he did, he wrote a library that uses a compiler and tracings, SIMs, single instruction, multiple data, basically the ability to process massive amount of information much more rapidly. And the point of doing that using all sorts of special CPU instructions, the whole point of doing that is to compress numbers. And then you realize, why do I care about, I have a really efficient way of compressing numbers. But then you realize, hey, compressing numbers, if the numbers are lookups for matches for particular result, that means that I have a much better way of storing information that I need to be able to do a query. And the ability to compress and decompress it on the fly means that the performance that you can give to the user is significantly better. And now you realize that, oh, wait, this is fast enough that I cannot measure that. So the cost of reading the data and the cost of decompressing is the same. It's again, you asking me, what would I say to the person 15 years ago? I would say this is going to be incredibly hard, really complicated. And at the same time, this is super interesting because you're doing something that is concrete and understandable. It's not, oh, I need you to be able to implement tax rules based on new sales tax that happen in this school region. So in this jurisdiction, you have this sales tax or whatever. So now you have to do that. And it gets super complex, but it's not straightforward. In databases case, in most of the things that I deal with is, okay, this is straightforward. It may be complicated. To give you some example, in RavenDB 6.0, we implemented sharding. Now, this is a feature that we actually had in 2010, and it's not a new feature for distributed databases. But when we implemented that, one of the things that we wanted to do is to take upon ourselves the complexity of managing, splitting the data among multiple nodes and how you manage that. So as a user, you don't have to be exposed to that. So the goal is very simple. All simple things are complicated. And you have to ensure that in a distributed environment, you're doing that and you're consistent and a whole bunch of other details like that. But it also makes sense. It also is something that you can measure. Okay, I run a benchmark and I can see that I'm 5% better than what I used to do. And that is a really gratifying approach.
I can imagine. I was going back to where I was saying that a lot of developer jobs are forms over data and maybe doing CSS or whatever and stuff. And this just sounds so gratifying. It sounds a nightmare in one way because of all the things you've got to think about, but it sounds fascinating at the same time as well. A quick question about so when you're talking about the trees and how you can walk the tree and things, and I'm thinking presumably on disk, do you have a concept of encryption? So encryption at rest. So how does it walk a tree if the data is encrypted?
Okay, so the idea here, so there are three types of encryption at rest that you care about. The data is encrypted, and in order to read it, you have it's about who can read the data and who can operate on that. So at the highest level of security, I'm giving you a blob. Here is my social security number. Here is my credit card data. I encrypted that on the client side. You just store that for me. That's it. As a database, I have no visibility into what's going on. About the most that I could do, I could maybe be able to look up an existing value because you said, okay, give me all of the users who have this, this credit card number. So that's about everything that I can do here. And even that is very suspicious from a cryptographic environment. So basically just storable. Next level is something called searchable encryption. And there are a cryptographic method that maintain the sort order of encrypted text, which allows you to do certain levels of queries on them. From my perspective, this is utter nonsense because it's trivially easy to go from, I have two encrypted texts and I can figure out which one of them is higher than the other. come after the other, to figure out what is the value of the text. Because what I'm going to do, I'm going to say, oh, let's say that I encrypted your name. So now I'm searching, okay, I want to give me everything that is bigger than M. Okay, you're not there. So now give me everything that is bigger than F. You're not there. Okay, give me everything that is bigger than C. You're there. Okay, so I know that you're between C and F. And then I just narrow it down, simple binary search or something like that. There are caveats. I'm explaining that in a very, very high level way. But basically, to this point, searchable encryption is not something that you really want to have. Finally, you have the notion of encryption at rest. And encryption at rest basically meant to protect you from one thing. Someone coming into your data center and stealing the hard disk. And with encryption at rest, and this may be literally someone stealing the hard disk, or maybe someone discarded an old drive. So for example, I mentioned earlier that we have the build servers and the drives die on a regular basis. So we replace them and we throw them away. And if we did not wipe the data correctly, you could presumably get something of them. In our case, okay, you want to see old builds of mine? Don't care. That is secret there. But if this is, transaction data or healthcare data or something like that, that is kind of important. So this is what encryption at rest is meant to protect you from. And the way that it works, a database, when it looks at a file, it doesn't look at the whole file as one go. It looks about it in pages. And the idea here is that each page was encrypted using its own key, there's a whole bunch of details, but it was encrypted. Now, when you read the data from the disk, you read the encrypted data, decrypt it in memory, and keep on using that. And once you write it to disk, you encrypt it, do it this way. So it's actually completely transparent for most of the database engine that you're writing and you're working over encrypted data. We don't actually care about that. And it's a really beautiful thing to see in this case.
So do you, like you talked about trees before, do you store the data with a tree or is it like non-clustered?
Okay, so when we're talking about databases, then we have the notion, there is the first mention of B-trees in the industry is from 1969, and the paper is called the ubiquitous B-tree. So in 69, it was already used everywhere. And if you're not familiar with how B-trees work, I would very strongly recommend go and read how they work. It is a really, really simple algorithm, and it has many variants, but it's super useful.
And B-tree is not binary tree, it's balanced tree, isn't it, I think?
There is a B-tree, B+tree, B* tree, B superscript W. There is a whole bunch of variants. But they are not balanced trees. Or I don't actually know if it's balanced. There is binary tree, which is what you're familiar with, which require you to do rebalancing. AV or a black tree. B-tree is basically work in fixed size buffers, typically a page size of 4 kilobyte to 8 kilobyte. That's the common numbers. And you're trying to pack as much data into as little space as possible. And when we're talking about, you mentioned cluster and uncluster. You tend to read about them. And, this is where whatever the database keeps the data in order or not in order or something like that. And it doesn't really make sense until you realize what's going on. So the basic idea is in a B-tree, the question is, what do you put at the leaf? Whatever you put, the data itself or a pointer to the data. And that has huge implications. For example, let's take Postgres and MySQL as two examples. Both of them don't store the data inside of the tree itself. You have a pointer. But there's a question here, what sort of pointer? So in Postgres, if I remember properly, if you have an index on the name field, the value that you would have in the tree is going to be the primary key for that name. In MySQL, you would have the offset on the file for that entry. And that leads to a very simple mechanism in which you're working. In Postgres, as you run the tree of the names, for each entry that you have to do another lookup in the primary key tree. In MySQL, you don't have to do that. With Raven, internally, we use non-cluster trees, basically. And we store the offset to the value in the file. And that matters a lot because it means that we can scan through a tree to find all of the matches. And now I have a list of positions in the file that I care about. And this is where you start having lots of fun with the database implementation, because now I'm able to say, okay, I have, let's say, 200 items that I read from this page, and they are located all over the disk. I can do something called prefetching and let the operating system know, hey, I'm going to be needing all of those, already start doing this work, and amortize the cost of going to disk in this fashion. So when you're looking at the internals of a database engine, it's very easy from the outside to consider this to be magic. When you go and start looking from the inside, there is a huge amount of smarts that is going on, but most of that is actually just, call it due diligence, or just the sort of work that you need in order to get things working. Most of that is not super complicated. And most of that you can start doing with CS 101. Eventually you get to the point where you start looking at, like Daniel Amir and his work and the sort of thing that he's doing. And this is super complicated. But then again, you realize that, okay, I have this super complicated piece, but it's basically just two functions, compressed numbers and decompressed numbers. And that's it. And it fits very nicely into the rest of your architecture.
So do you find like obviously we've spoken about all this complexity that you have to deal with. If we now look at a developer using RavenDB, when they're writing queries, for example, what are like some like really big common mistakes you see people make which might heavily affect performance and that kind of thing?
So this is an interesting question, because the reason RavenDB exists is specifically for this reason. Because I got sick and tired of having to support the same sort of errors time after time after time. And probably the most classic example of such an issue is when you run a query and it didn't create appropriate indexes for that. A database engine at this point have two options. It can reject the query, saying I have no way of actually executing that efficiently. Or it can say, okay, I'm going to start scanning through all of the records in the database, which can be really expensive. Now, the really, really sucky part about this is that as a developer, I'm working on this. I'm working on small data sets and powerful machines and one user. It's entirely possible that my queries are expensive and I'm not even seeing that. But put that on production servers, lots of data, lots of queries, and suddenly the performance drops because you're asking the database to do a huge amount of work. At which point you have to call an expert, and that expert is hopefully going to say, oh, you're missing this index or that index, something like that. With Raven, the thing that we did is to say, hey, if I'm going to scan through all of the records anyway, I'm going to go ahead and create an index for that. So the next time you run a query, it's going to answer that from the index. And basically, just this feature, and I explain it in a couple of minutes, but just this feature means that as you write queries on top of RavenDB, you're providing RavenDB with additional information about your environment, and it is able to create the appropriate set of indexes and the appropriate behavior in order to optimize your system. Which leads to another really interesting problem. You cannot do that on most databases, because the process of creating an index is super expensive. It may lock the table, it may consume a lot of hardware resources. So this is something that in production, create an index, the head DBA does that after he fasted and meditated for a few weeks, etc. And even then you schedule a downtime and all sort of stuff like that. With Raven, from the get-go, we says, hey, I need it to be efficient. And I need to be efficient, not from the point of just raw latency or something like that. You have to do that, but think about the developer productivity aspect. So with Raven, we design our indexes from the get-go to, I'm able to go into production system and create an index and rest assured that this is not going to kill the entire system. And that means that I'm able to create indexes on the fly, which means that I have to ensure that my indexes are suitable for running in production, and the cycle continue. So you have a very strong feedback cycle to allow you to do the software optimizations without making the assumption that you have a developer who knows what they're doing or DBA on call process and those sort of things. I mentioned sharding as a feature that we now have, which is new, even though we had it in 2010. And the reason we have this sort of feature is it took us a lot of time and effort to be able to enable that scenario without dumping this huge lot of complexity in your lap. So now you are able to go to the RavenDB studio. It's okay, I want it sharded, I want it on these databases and this application factor. And then, okay, and now I've done that. It's working like this. And the rest of my code doesn't change. And unless I'm doing something super weird, the progression of complexity in my system is a linear progression and relatively smooth at that. Whereas in other cases, okay, I built my system. Now I have this huge exponential complexity of, okay, now I need to understand exactly what's going on, so I'm able to optimize this efficiently. And in many cases, those are not something that you can do. Think about the interaction between your application and the database. So let's say that you're using microservice architecture and you have all of these sort of services that expose using REST, etc., and you're consuming them from the client side. So from the client side, in order to render a page, you start issuing, okay, give me from here, and compose that. And from an architecture perspective, this is wonderful. From a practical perspective, it means that loading a single page means 50 to 100 separate requests, each one of them making multiple requests to the database. And you're looking at that and says, okay, there is really very little I can do on a per request basis to optimize that, because now you have to do a completely big shift in the architecture of how you're working. And that is unfortunately the reality. So you have to be able to operate without, this all-seeing DBA that can optimize everything. And you have to still be able to provide good solution even under suboptimal architecture.
And you mentioned something called RavenDB Studio then as well.
Mm-hmm.
And that might half answer my question, but going to indexes, if RavenDB is creating indexes, is there like a GUI or tool that you can visualize what's been created?
Yes. So part of making operation easy is making them visible. So with RavenDB, it is operating over HTTPS or HTTP, and you can point your browser to the RavenDB instance and it will give you a GUI. So you don't need to install anything else. And that GUI gives you monitoring capabilities. We also did things like, let's analyze common issues and raise them to you. For example, if you're running on the cloud, it's very common that you're running on really crappy hardware, especially disks. So now you come to us and says, hey, my system is slow. Why is it slow? And this is the worst thing that you could possibly try to debug. So RavenDB measure your I/O, your rates, and if we're seeing that, hey, I try writing to the disk and it took 30 seconds to write 1 megabyte, which is entirely possible in the cloud, I'm not going to hide it in some log somewhere that you have to know to read. We're going to show that you here's alert in the studio that, hey, at this time, at this place, this is what we had. You can correlate that to your storage metrics and then go to, hey, I need a better disk. Instead of, okay, let's support now a support call and hold up everyone for 3 weeks while we try to get lower and lower in the stack to try to understand what's going on.
That's pretty cool. And there is a Docker container as well, so you can just spin it all up, presumably, and have a play.
Yeah. You can use Docker, Kubernetes, Helm charts, what else? Terraform. You can use it. We actually have a free cloud instance So you can have your own private cloud instance to play with RavenDB. We're trying to make it as easy and approachable as possible. And the idea is that you don't need to really think how you're doing that is paramount. You sit down, you start, and it's working.
That's really nice. And it's written in .NET as well. So win-win-win. So about 10 minutes ago, you did say that you only had about 10 minutes left. Do you have time for dev picks at the end?
So in terms of dev picks, I would strongly recommend go and read the Daniel Lemir's blog. Fascinating topic, especially if you care about performance. We ported his sim compression library to C#, and it is amazing performance. Beyond that, there is a short paper, like 5 pages by James Mickens called This World of Ours. He's a researcher in Microsoft. And this is a paper about security. And his thesis there is that Mossad or not the Mossad, whatever you're dealing with, a nation state or, John from across the street who is a script kiddie, and the difference in system that you have to deal with. Basically, by the way, he's hilariously funny and very accurate, but everything from James Mickens or Daniel Lemire tend to be pure gold.
I'll definitely include those in the show notes then. So my dev tip is actually a Twitter handle, and I'm sure all of the listeners have heard of David Fowler, but he tweets out lots of really interesting, just thought-provoking tweets with code snippets about things like memory allocations and all this kind of thing, which has lots of replies and gets lots of people talking. So a lot of his tweets are getting a lot of conversations around low-level C# and .NET stuff. And it's just, there's some fascinating threads in there. So, in fact, no, I said Twitter, didn't I? I've got to call it X now. And why has it been called X? Yeah, so it's just, and I think he's on other ones as well, but yeah, it's definitely worth checking out. So before we head off, where's the best place for listeners to reach out to you if they've got any extra questions?
Oren at RavenDB.net. I'm writing that here.
Cool. And we'll include links to all your stuff in the show notes as well. So with that, just a massive thank you for joining me. It's been quite fun digging into the database internals. I think I'm going to be having nightmares for the next few days, just picturing having to deal with all that, but it sounds fascinating.
Thank you. Thank you very much.
You're welcome. And thank you everyone for listening. If you've enjoyed the podcast, please do help me spread the word on social media. I normally use the hashtag unhandledexception, and I can be found on, now not Twitter, X, at Drakan. And my DMs are open, and my blog is danclark.com, which has links to all my social stuff too. And we'll include links to all the stuff we've mentioned today in the show notes, which can be found on unhandledexceptionpodcast.com.